Giuseppe will tell us about definitions for predicate.
Okay, thank you. So this is the content of the talk. It's about a work in progress and some discussions and some work I've done with Manuel Barbosa, Angelo De Caro, Puya, Fashim, and Vincenzo Ioino. It's about results on simulation-based definition for secure predicate encryption. So let's start from the beginning. Okay, so what do we want from a secure encryption scheme? This is a quote from the Goldwasser-Micali paper on probabilistic encryption that started, that put encryption on solid foundation. Essentially, they said that an adversary who knows the encryption algorithm and is given the ciphertext cannot obtain any information about the clear text. And in these two papers, which one is the conference and the other is the journal version of more or less, they gave two formalizations. Okay, let's start from syntax. Okay, so an encryption scheme, just to set a notation, encryption scheme is just three algorithms. The key generation algorithm that outputs public key and secret key, an encryption algorithm, and the decryption algorithm. And there is some obvious correctness that if you encrypt something and you decrypt, and you encrypt it with the public key, and you decrypt what you obtain with the associated secret key, then you should get the message, except with some very small probability. And then this is formalization. That was syntax. This is semantics. So what is the formalization? What is a secure encryption scheme? So Goldwasser-Micali gave two different formalizations, which I'm going to rewrite, and maybe it's not going to be exactly the same, but this will help us during the talk. One is game-based and was called, I think, indistinguishability or polynomial security. And it's a game between an adversary and a challenger. And the challenger generates a public key and a secret key and gives the public key to the adversary. The adversary does his computation on the public key, and then it outputs two messages, M0 and 1, of the same length. And so the intended meaning here is that, okay, he feels is very good in distinguishing encryption of M0 and, from the encryptions of M1. And then the challenger picks one of the two at random, encrypts it, and sends the resulting ciphertext to A. And then A gets the ciphertext, and it outputs his guess B prime. And then we say that the adversary wins the game if B is equal to B prime, wins an instance, a run of the game, and then the adversary breaks the encryption scheme if it wins with probability significantly greater than 1/2. Of course, you can always guess with probability exactly 1/2 by outputting the random bits here. Okay, so this is all well known. And then we say that the encryption scheme is insecure if no probabilistic polynomial time algorithms can break it. And then there was a second definition, which is which I'll call simulation-based. The paper was called semantic security. It's not exactly this, actually. It's not this at all, but this will be helpful for the rest of the talk. So it has two experiments. One is called the real world, and the other is called the ideal world. And essentially, in the real world, the adversary gets at the end, so there is no pointer here, okay. And the adversary gets in step 3 a ciphertext over a message M that has been chosen by the first part of the adversary, while in the ideal world there is a simulator that does not know M, only its length, and that outputs something, a ciphertext prime. And then I want these two experiments to give output, and these two outputs to be indistinguishable from polynomial time machines. And Yeah, and so you can get different definitions, whether depending on the way you quantify over adversary and simulators. Okay, so I'll try to gloss over all of these details, but you can have black box, non-black box, and all of this. What is interesting here is that Goldwasser and Micali proved that an encryption scheme is semantically secure if and only if it is insecure. Essentially, that the game-based definition is as strong as the simulation-based definition. So one direction it's easy, and the second direction, proving that insecurity implies semantic security, it's a little more interesting, and actually we're going to work on this. So I have here 2 lines just to remind all of us what was the proof. And then essentially the proof, so I have to come up with the simulator, and then the idea is that the simulator gets the message, the length of the message, and jump picks arbitrarily any message, M prime, encrypts it, and returns CT, the ciphertext, CT prime. So the simulator computes this for an arbitrary message M prime, okay, all zeros or I don't know, all ones, whatever. And the idea is that now the difference between the 2 experiments is that in one experiment the adversary sees an encryption of M, in the other sees an encryption of M prime, and if there is a distinguisher between the 2 experiments, then you can build an adversary for the game-based definition, in which the adversary outputs M and M prime, then one of the 2 is chosen, and then depending on which one, then we are in the real world or in the ideal world. Okay, that's very interesting. So this was the original goal, and we feel quite satisfied about the original goal. This has been successfully reached. We have a good theory, but then new questions were asked. So one point, we know we can control that 0 information is leaked by the ciphertext. And then we became a little bit greedy, and then we wanted to say something more sophisticated, something like, can we control how much information is released by the ciphertext? Essentially, can we give different adversaries, different tokens, different keys, so that it can extract different bits of the plaintext or compute different predicates of the plaintext? So why do you want to do that? So there are several scenarios in which something like that will be useful. So this is a very common scenario. Like, for example, we all use Gmail, or I use Gmail. And okay, so me being Alice, I keep my email on the Gmail server, and then I don't actually do this, but if I was, I should have. But then I could ask all my friends to encrypt the email using my public key. And then every time I get a new message, so I go to Gmail, I download the message, decrypt and read it. That's very useful. What's a little bit of a problem is that Gmail allows you to search for your emails. Okay, so when I was planning my trip here, I was searching for SASW, and then I got all the information, and then all of this. So if the email was encrypted, so for example, suppose that Alice wants to download all the messages which have subject, in the subject field they have project X, okay, whatever it is. Okay, so if the email is encrypted, and then I want to perform a search on encrypted emails, then there is no way other than downloading all the messages, decrypting all of them, and then once they are decrypted, I do my search, and I search for project X. Then, of course, this defeats the purpose of having all emails on Gmail, because try to do this with your iPhone or your iPad or your Android. That's not very, it will take a while, okay, to download all your emails. Like I have more than 1 gigabyte of emails on Gmail. Okay, so that's where predicate encryption comes to help. Okay, so let's fix some terminology here. We have a functionality. A functionality is a two-argument, and for the purpose of this talk, I assume it's a predicate. So it takes two arguments and returns a bit. And the two arguments are one from a key space K and one from a message space M. Essentially, M is the message, and K describes the function that you actually want to compute on the message. So let's see what is a predicate encryption scheme. So now we have four algorithms. One is setup. The setup outputs a public and a master secret key. So in my email scenario, so I run setup the first time I enroll into Gmail, and then I publish my public key on my website, or I give it to my friends, and then I keep the master secret key for myself. Okay. Then the encryption works like a regular encryption. Like if a friend wants to send me message M, it just picks my public key, encrypts it, has a ciphertext, and then sends the ciphertext by email. Okay, the two differences now is the key generation algorithm and the eval. The key generation algorithm outputs a token for every possible K in K. It's a probabilistic algorithm that takes a master secret key and outputs this token. And the eval algorithms instead takes a public key, a ciphertext, and a token, and computes the function fk of m. So if the ciphertext is a ciphertext for plain text m, and the token is token for key k, then you can evaluate the function fk of m, fkm, on the ciphertext. And notice that to evaluate this function, you don't need a secret key. So, going back to the Gmail example. So what do I do now? Every time I want to do a search, for example, then and I want to compute, for example, all messages that satisfy certain criteria. So I just generate the token and I send it to Google, and I instruct Google to select all messages for which eval returns 1. Then Google selects all the messages, sends me all the messages, and then I decrypt only those messages, only the messages that are related to Project X. Okay? Okay, so this is just an example, very, very simple example, but then you can think of zillions of applications on this. So, how do we define security for predicate encryption? Okay, the first thing is to have a game-based security notion. So you have again, you have a game between the challenger and the adversary, and the challenger generates a public key along with the master secret key and sends the public key to the adversary. And then the adversary adaptively asks for tokens for K1 and then K2. He gets a token for K2 and then he does his own computation and again say, I would like to see K3 and so on. And all of these tokens allow the adversary to compute FK1, FKQ1, and then he can plug in any ciphertext he wants. He can generate his own ciphertext, whatever. Then after a while, he feels strong, and then he says, okay, I want to be challenged on two messages, M0 and M1. M0 and M1 have the same length. Okay, the challenger says. He picks one of the two, encrypts it, and sends it to the adversary. And now the adversary receives the ciphertext. He can ask for more tokens. And then after a while, he outputs his guess, B prime, his guess for B. And now we say, as before, we say that A wins if B is equal to B prime, and the two messages M0 and M1 have the same values for all the functions that the adversary is allowed to compute. So now the adversary is allowed to compute on ciphertext all of these fk1 up to fkq. And now, of course, if m0 and m1, there is one of these, there is fki, for which m0 and m1 give two different outputs, then of course you can apply the eval algorithm to this challenge ciphertext and decide which one is which. Okay, so then, so we say that A wins if B is equal to B prime and the tokens he has received do not allow him to tell apart M0 from M1. And then again we say that A breaks if he wins with probability significantly larger than 1/2, 1 over poly in the security parameter. And then we say that this scheme is insecure or game-based secure if no probabilistic polynomial time algorithm breaks it. That's the definition. So this is straightforward from Goldwasser-Mikari, more or less, with one extra point that you really want to ensure that the adversary doesn't get keys that allow him to discriminate between the two messages, the two challenge messages. So this is a nice observation, game-based secure encryption is exactly game-based secure predicate encryption, where the adversary, so the key space has only the empty string, epsilon, and f of epsilon and m for any message m is the length. So essentially, the secure encryption is simply predicate encryption that leaks the length of the message. So this was known from before, essentially. So these are some functionalities that for which implementations have been given. So the equality functionality, in which the key space and message space are strings of L bits, and the predicate returns 1 if and only if k and m are equal. This was considered in a paper in Eurocrypt by Bonnet, Di Crescenzo, Ostrowski, and myself. And then I think Bonnet and Waters considered hidden vector encryption, which is easily seen to be a generalization of equality. It's much more interesting than equality because it has, messages are still binary strings of a fixed length L. And the keys now have 0, 1s or stars. Stars are don't care symbols. And we said that fk and m is equal to 1 if in every position either the key is a don't care, or if it is not a don't care, the key and the message agree in that position. Okay? So fk and m is equal 1 if and only if ki is star or ki is equal mi for all I equal 1 to n. And this was introduced by Bonnet and Waters, and I think the definite implementation in the game-based is by Okamoto and Takashima in the coming Eurocrypt. And in the coming pairing, we have also an implementation. Obviously, HVE implies equality. Equality is simply HVE without stars. Okay. And there is another inner product, and there is another functionality that has been studied, and which I'll talk about in the talk, which is the inner product. Here, keys and messages are vectors over a final field, Zn. And the functionality fk of m, fk and m is equal to 1 if and only if the two vectors k and m are orthogonal. Okay, that means that that sum ki mi is equal to 0, where all operations are done modulo n. This was introduced by Katz, Sahai, and Waters in Eurocrypt a few years ago, and Okamoto and Takashima have the definite implementation in the coming Eurocrypt 2012. There is an interesting observation by Katz, Sahai, and Waters. It's about the relation between inner product and HVE. Essentially, inner product implies HVE. We'll see later what this means. And then, I think last year in TCC, Bonnet, Sahai, and Waters, they gave an example of a very simple predicate encryption scheme, which you look at it and you say, okay, This is insecure, but it actually meets the game-based definition. Okay. Oh, okay, it's none of these. It's an ad hoc predicate encryption. But then, so this means it's time for a simulation-based notion of security. Okay, and now we look, and now I'll give you one definition here. This is not the BSW definition. It's a definition that when I was writing the slides, I looked at GM, the definition of the simulation-based definition in GM, and then I came up with this. And then, okay, so we'll talk about this definition here. I have a slide that points some differences. Okay, you see, it's like we still have real world, the ideal world. In the real world, the adversary gets a ciphertext, and the adversary is allowed to ask for tokens. You see, A0 has oracle access to the key generation algorithm with the secret key, and they're called K1 to KQ, the tokens that he has asked and he has received. And now the simulator in the ideal world gets the public key, gets the length of the message, and gets the specifications of all the functions for which the adversary has obtained the token, plus the output of the function on the message M output by the adversary. And then essentially the simulator's task is to simulate a ciphertext CT prime. Okay? So here you have a slide. The BSW definition is a bit different from the one we are going to discuss in this talk, because, for example, the public key in the ideal world is generated by the simulator in the BSW definition. Here instead is honestly generated. The adversary doesn't output a single message, but it outputs several messages, a sequence of messages, and also here. And the BSW definition, also A1 is given access to the token generator algorithm, the key gen. Here I just give access to the first one. Okay, this is not much of a problem because well, I'm going to use this definition essentially to give negative results. So still, I cannot say which definition is stronger, which one is weaker, because BSW gives more power to the simulator because it lets the simulator generate the public key and the secret key, but also gives more power to the adversary. So let's take the GMW, the GM, proof of equality between game-based and simulation-based, and let's try to make it work in this new scenario. Okay, so suppose the simulator just picks an arbitrary message and encrypts it. It's going to break down. The proof is going to break down because consider this adversary here, A0. A0 and the A1 communicate via aux, auxiliary message. And suppose A0 puts in this auxiliary message all the tokens he has received. Then the adversary A1 in the real world, this prime here belongs here actually. I'm sorry about that. So in the real world he sees a ciphertext of M. And then if he evaluates, if he runs the evaluation algorithm on the ciphertext CT that he receives with all of his tokens, he gets the value FKI of M. While in the ideal world, the adversary A1 gets CT prime here, which is an encryption of M prime. So if he runs the evaluation algorithm on that ciphertext with the tokens he gets from A0, from his friend from the first stage, he gets FKI of M prime. And then, of course, the two distributions are going to be different unless M prime is such that it coincides with them with all of these tokens. Okay, so now we have the following ideas. It's called pre-image sampleability. So we have a functionality, and we say that the functionality is pre-image sampleable if the following happens. there is an efficient sampler, we call it SAM, such that for all efficient adversaries, if the adversary outputs a length of a message and then it outputs the description of Q functions, K1, KQ, and the output of these functions, B1 to BQ, then the sampler can output a message M from the message space such that this holds. So this is very similar to a notion introduced by O'Neill. It's called pre-image sampler, but there are some differences between the two notions. But the spirit is the same, actually. That's where I got this idea. Now, if the function is pre-image sampleable, then the simulator can do the following. When he has to simulate, he gets public key, length of the message, he gets K1, FK1 of M, and so on. And then it just runs the sampler on input M and all of that, receives M prime. Now M prime might be different from M, but what is important is that M prime gives the same results for all tokens, for all functions that the adversary can evaluate on the ciphertext. Yes?
In the previous definition, I would imagine for most, in the pre-image sampleability definition, I imagine for most predicates, there will, if you ask enough questions, there will be no message at all.
Yeah.
So do you want to maybe say that in the first stage, the attacker has to output a consistent message? Because that's enough for you. Because I'm just saying...
Yeah, because I'm going to apply only to adversaries that are going to be consistent. Yeah. So this is a simulator. And I can adapt the proof from O'Neill to show that if a functionality F is pre-image sampleable, then semantic and game-based security notions coincide. So a scheme is either both or neither. The converse does not seem to hold, and then I'm going to give evidence that the converse doesn't hold. So now, let's go back to our three functionalities, and then we see that the inner product is actually pre-image sampleable, which is very good, which means that the Okamoto-Takashima construction is actually semantically secure. That's very easy to see because what is the sampler for inner product going to be? He receives a sequence of vectors and bits, and then he has to solve this system of equations in X over Z and L. And this can be done very easily. Okay, that's good. So hidden vector. Now let's redo the definition of hidden vector here. So now I'm going to call the functionality the match functionality, and then I have two vectors, y and x, and then I say that the two vectors match if yi is a star or xi is equal to yy, and they don't if otherwise. And then here I have some examples. For example, these two vectors not match because, for example, they do not agree in the first coordinate, and while these two match because they agree in all coordinates except here, but there is a star in y. Okay, now I'm going to show that if hidden vector encryption is pre-image sampleable, then 3-SAT can be efficiently decided, which I take it as an indication that is not pre-image sampleable. So I'm going to do the following, like you give me a formula phi, it has m clauses and n variables, and then I can construct an example, an input for the sampler such that if the sampler outputs x, then that x describes a truth assignment for phi. And I'm going to show this on an example, like I take a formula, this, and then I'm going to construct, I'm going to consider one clause at a time. And for this clause, see x1, x2, and x3, there is exactly one assignment to x1, x2, and x3 that doesn't satisfy the formula. It's 0, 0, 0. So I come up with the vector y1, which has 0 in the first three components, stars everywhere else, and b1 equals 0. I do the same for the second clause. Here, the second clause, there is one assignment that doesn't satisfy the second clause. It is x1 equals 1, x3 equals 1, and x5 equals 0. So I construct this vector y2, which is 1 star, 1 star, 0, and all stars, and then I put b2 equals 0, and dot, dot, dot. I do this for all of them, and then I do this for ym. And ym has 0 in position number 13, 1 in position 21, and 0 in position 34, and still bm is equal 0. Now I feed y1 b1, y2 b2, ym bm to the sampler, and I call x1, xn the output of SAM. So now look, now the match. Okay, now if I compute a match between x and y1, that should come to 0. Why? Because here b1 is 0, which means that x1, x2, x3 as a triple is not 0, 0, 0. So either x1 is 1, or x2 is 1, or x3 is 1. Since 0, 0, 0 was the only assignment that didn't satisfy the first clause, this means that the first clause is satisfied by x1, x2, and x3. So, okay, now I looked at a match between y2 and x. Again, by the properties of the sampler, the match should give 0, which means that x1, x3, x5 is different from 1, 1, 0. You see? x1, x3, x5 is 1, 1, 0. Not to match this vector, you have to be different from 1, 1, 0. Since that was the only assignment to those three variables that didn't satisfy C2, and x1, x3, x5 is different from that, that means that C2 is also satisfied. Evgeny, you feel uncomfortable.
No, like I thought you want to satisfy to set match to 1. Why do you set match to
because here y1 encodes the only assignment that does not satisfy C1. So I want the output of sampler not to match this, and if it doesn't match the only non-satisfying assignment for C1, that means it's going to satisfy it.
But shouldn't the sampler, pre-match sampler output satisfying assignment?
No. Look. The sampler is going to output x such that if you take the match of x and x1 and y1, it's going to give you b1.
Oh, you can put the bits, I see.
Yeah.
I miss the bits, okay.
Okay?
No problem.
So that's done on purpose. Okay, now should be clear that also the last clause is satisfied, which means that x satisfies phi. Okay? And now depends, okay, if sampler is probabilistic, then it means that 3 SAT can be decided in probabilistic polynomial time. Still, we don't believe this to be true. So we take this as a sign that HVE is not pre-match sampleable. Of course, I told you that Katz's high waters prove that IP implies HVE. Okay, so what does this mean? Essentially, it means that I can translate one into the other. Essentially, there are two reductions, one for the message, one for the token, with the following property. That if I take x and y, which are messages and token for messages and functions for HVE, I can transform it into message and token for inner product and maintain the predicates so that y and x match if and only if the reduction of x and the reduction of y are orthogonal. Okay? So RMS and R token, they are both in ZN2L, so you double the length. But this is not a problem for. Which means that you can do the following. You can construct HVE from IP in the following way. So a setup is like IP setup. You run the IP setup. For example, you can take the Okamoto Takashima and then run the IP setup. When you encrypt X, you don't actually encrypt X, but you encrypt the reduction, or what you get from the reduction, RMS of X. when you generate a token for y, you don't generate a token for y, but you generate a token using the IP key generator for the reduction token. And when you test the ciphertext and token like you did in IP. Now the simulator is very easy because the simulator now gets PKM and YIs and runs the sampler for IP, which we know it exists, and encrypts using IP what it gets from the sampler. So there is no contradiction between this and the previous, because here I'm not using pre-image sampleability. I'm just saying that pre-image HVE is not pre-image sampleable. I'm not saying that there is another way of getting semantic security for a HVE going through IP. Okay. In fact, the simulator here does not encrypt using the HVE algorithm, but encrypts using the IP algorithm. In a sense, this is a bit unsatisfactory because we are saying like that HVE is not pre-image sample, but in a sense the simulator is cheating because it's using the IP encryption algorithm that is supposed to be used only on output from the reduction on something that might not come from a reduction. So I introduced the following concept, the concept of robust predicate encryption. A robust predicate encryption has an extra algorithm that is called validate. And the validate algorithm essentially checks that the ciphertext has been obtained from encrypting a real message from the message space. Okay? So for example, if XX here is not an output of the reduction, which most probably won't be, then the ciphertext obtained from encrypting it should not pass the validation algorithm. So robust essentially means that when you get a ciphertext, that's really a ciphertext for a message from the intended message space. Okay, so I have some conditions here that there exists a message. If a ciphertext passes the validation, there exists a message that was used to encrypt it, and then if you do the test with all possible tokens here, you get the answer that are consistent with them. For example, what we observe that the reduction through IP does not give a robust HVE. Okay, so robust is interesting because now we can prove that robustness, for robust predicate encryption, being pre-image sampleable is actually necessary. I have a sketch here. This is the ideal world. And here are a few observations, like if you take the simulator here, CT prime, this, the ciphertext output by simulator CT prime, this must pass the validate algorithm because the ciphertext in the real world passes the, so if you have a good simulator, then CT prime must pass the validation. So that means it's the encryption of the message M prime. And if it's an encryption of message M prime, then when the adversary is going to test the ciphertext CT prime with all the tokens that he has received by querying the key generator oracle, it's going to get answers that are consistent with M prime. But then this should be also the same with the message M, with the answer with the message M, which means that M prime and M are the same here, which in a sense robustness forces the adversary, the simulator, to output CT prime, that is a ciphertext that coincides, it's a ciphertext of a plaintext M prime that coincides with them in all tokens. And then we can build a sampler out of the simulator, we run the simulator, and since we know the secret key, then when the simulator outputs CT prime, we decrypt and we get M prime. And M prime has this property, which is exactly what the sampler will do.
So in your definition of pre-image sampleability, should the sampler output the message or the ciphertext?
No, should output the message.
It's not clear he can output the message, he can only output the ciphertext.
Yeah, but that's the simulator. So the sampler is going to run the simulator,
Yep.
and the sampler is going to generate the public key and secret key, runs the simulator, gets CT prime, and then decrypts.
Okay, you don't know the secret.
Yeah. Yeah, that's why I had the definition this way. Which means, okay, so now this is nice because now we know that for robust encryption, for robust predicate encryption, pre-image sampleability, which comes from O'Neill, it's necessary and sufficient. I only showed one direction, but the other direction is obvious from O'Neill. Which has some corollary, like for example, if HVE is semantically secure robust predicate encryption, then 3SAT can be decided efficiently. Notice this is an impossibility result that holds for single message and token non-adaptive adversaries, which means that A1 is not allowed to ask for tokens after seeing the ciphertext, the challenge ciphertext. Okay, what now? I still have 20 minutes. Okay, so essentially I've shown you that for HVE, the simulator always loses from the adversary, okay? Then there are two possible ways of proceeding. Either we weaken the adversary, or we strengthen the simulator. I'm going to pursue both directions to give you some results, some observations. So let's start from the weakening the adversary. The first thing, that there is this very simple observation that HVE is one pre-image sampleable. What does it mean? Like suppose that the sampler is only asked to output a message such that the match with Y1, YQ is equal to 1, which is exactly what we didn't do in the reduction. Now we have the following observation. If Y1, YQ, if there exists a message M for which Y1, YQ when always match, that means that if I take any position in which two of these vectors are non-star, that means that those two positions must be equal. And this gives you a very simple sampler algorithm, like I put x1 equal to the only one non-star entry that appears in the first component of all the yi's, 2 and so on. So it's very simple. And this gives a semantically secure robust HVA for adversaries A0 that are restricted to output X for which this holds. Okay, that's quite, it's cute, but not much more than that. Also, we might ask, what happens if we bound, if we know in advance the number of queries that the adversary is allowed to make? And here there is an interesting observation that if I have the following encryption scheme, like something that it's game-based secure with respect to Q-bounded adversaries, and it's for the following functionality. The functionality takes as a key a circuit, and then input circuits, and as a message, an n-bit message, and outputs the value of the circuit on that message. So essentially, you have predicate encryption for all for a set of circuits, NP. Suppose you have this. Okay, I have no idea how to get this, but then I'll show you that for this, for Q-bounded adversary, I can also build something that is semantically secure. So I define the following functionality. It's called M, that works on M prime and K prime. What is M prime? M prime as Q plus 1 is a tuple of Q plus 1 messages. So all messages except for the first one are n-bits messages. The first message can be either an n-bit message or a special symbol like bottom. Okay, and the key space has the same key as before, like all circuits, and an n-bit string. And the functionality f prime is defined in the following way. Okay, so now if R is equal to one of the mi's, then the functionality is going to output 1. If this is not the case, and M is equal to the special symbol, then the functionality is going to output 0. otherwise the functionality is going to output C of M. So why did I define that? This functionality has a very nice property, is that if I choose at random R, M1, MQ, then, except with negligible probability, the two functionalities coincide. Okay? So what I'm proposing is that if you have a functionality here, if you have a predicate scheme for this functionality, then you can build a predicate scheme also for this functionality, because here you have a predicate scheme for all circuits, but then I can implement f prime with a circuit. That's very easy from the definition. And then f and f prime, essentially they are the same functionality, except with very exponentially small probability. Then every time I encrypt a message M, I pick Q other messages at random and then encrypt those. And every time I generate a key for a circuit, I don't just generate a key for the circuit, I generate a key for this circuit here for a random R. And then the only way I can make a mistake in the evaluation is that one of these R is equal to one of these MIs, which is going to happen with negligible probability. Okay, this functionality also has another interesting property, is that this functionality is PS, is pre-image sampleable. So now, what is pre-image sampleable for this functionality? Okay, now the sampler receives C1, R1, and the bit B1, and then CQ, RQ, and the bit BQ. And it has to output a message, and the message M is Q plus 1 messages. The first message is going to be, the first component is the special symbol, and then you have M1 and Q, which are defined like this. MI is equal to RI if BI is equal to 1, otherwise it's equal to the special symbol. Now notice that if I take M to be the output of the sampler, then for every I, F prime CI-RI-M is equal to BI. So I managed to prove that there exists a new functionality that coincides most of the time with the functionality I'm interested in, and is pre-image sampleable, given a bound on the number of queries that adversary is allowed to make. Of course, it's clear from here that you really need to know in advance when you generate the public key and the secret, the public key that this is the case. Okay, so this is sort of a Feigl-Apitow-Shamir OR trick for encryption, essentially. You do this, you do the OR with something that is negligible probability, and then you use that negligible probability to cheat in the proof, essentially. That's the... Okay, so that's for giving, for weakening the adversary. Let's give more power to the simulator. So there are a couple of ways of giving the simulator more power. One way would be to give the simulator the secret key here. Oops. Yeah.
Just a global question. What is your goal? So you're saying if semantic security is not equivalent to indistinguishability, it's bad. So you want to make sure you look at predictions where they
no, there is no bad. No, there is no good and bad. I'm just trying to understand what's going on.
Oh, I see. So you want to
yeah. So I have one definition for this. I can prove that. Okay, I can characterize when the two notions are equal for robust. And now I'm trying, to explore. This is work in progress. It's just, brainstorming with all of you, essentially. Now I say, okay, so maybe we got those impossibility results because I was too nasty to the simulator. Maybe I should have given him more power. One way of giving him more power is to give the simulator the secret key. Still, the secret key is honestly generated. So this is not a BSW model. And if you look at the original GM definition, this is no problem in the GM definition. It's something that if you do it in the original definition, still everything works. Okay, but here we have a problem. Okay, We don't actually have a problem. Is that the nice theorem that we had before, that for robust semantic security, for a functionality implies that functionality is pre-image simpable, that ceases to be true. And I have a very quick example. Okay, one way of making something robust would be to add a random string in the public key, and then encryption is essentially encryption plus NISC. But now, if the simulator has the secret key, then it could have the trapdoor associated with the common reference string, with the random string, and then it can use that trapdoor to fake the simulator, essentially, to fake the sampler.
Why should the secret key contain the trapdoor for the CRS?
Oh, because that's
Publicly verifiable message, right?
yeah, it's verified. So that's the predicate encryption scheme I'm defining. This is a predicate encryption scheme which is robust and for which PS does not hold. And you have semantic security, okay? And essentially the simulator uses the sampler from IP and then he fakes the NISC. So this is an example of, so this is a specific construction of HV which is robust and is semantically secure. Okay, so it breaks the previous scheme. Okay, that doesn't seem to be much of a problem, but so maybe we should give a little less power to the adversary. And then we have, so I decided to do the following. I don't give, the adversary doesn't receive the secret key, but he receives exactly the tokens that the adversary has seen in the real world. And now something very strange happens, because now I can construct a scheme which is clearly insecure, but which meets this, this definition, which is a clear indication that this is not a good definition, I guess. Okay, so yeah, we have 5 more minutes. So let's go through this construction. So this is a very ad hoc, and it's a bit inspired by the counterexample in the BSW paper, the counterexample for game-based. So let's see what it does here. So I have a family of trapdoor permutation, FK, okay? During setup, I pick one of them, K, and I put it in the public key, the description of the function in the public key, and then essentially I'm saying that okay, you can get a token for computing Fk of M given a ciphertext that encrypts M. Okay, but I'm doing it the stupid way. Like if you see the key generator for function K just returns the master secret key. What is the master secret key? The master secret key contains the secret key of the encryption scheme and the trapdoor tau for K. And how is the evaluation going to work? Like you take the token, you take the ciphertext, you decrypt it, and you return Fk of M. Okay? So clearly, this shouldn't be secure, because here during the evaluation, the adversary doesn't learn just Fk of M, but it learns M, and it shouldn't be allowed to learn M. So this is clearly not secure. But unfortunately, if you give the adversary the tokens, then this is going to be secure. Why? Okay, so since there is only one functionality, the adversary either makes 0 queries or 1 query. The only functionality for this is the functionality that allows to compute the special K that is in the public key, the special Fk that is in the public key. So now for key equals 0, simulation is easy because the adversary does not have any token, and then I just encrypt any message of the right length, and the simulation goes through. If instead the adversary has asked for the one token that is allowed to ask, This means that the simulator gets the token. Not only gets the token, but he also gets the output of the function on the token. And now if you remember, like the token was so badly constructed, the token has the trapdoor for the function. So now the adversary gets fk of m, that is the value of the trapdoor function of the message m, and he gets the token, and the token contains the trapdoor, so he can invert fk of m, get m from fk of m, and then can encrypt it, and the simulation is perfect. So essentially, like if we give more power to the simulator, then it seems that at least for the two obvious ways of giving him more power, then we run into problem. Of course, this example also applies to the previous case where we gave him the simulator the secret key, because now if you give him the secret key, then he can generate the token by himself. So if we give more power to the simulator, then we run into problems. So maybe there is another way of giving more power to the simulator, still go around the impossibility result. And if we weaken the adversary, then okay, I showed you a couple of ways of weakening and getting some results. And this is more or less what I wanted to say. Thank you.
Any more questions?
You're describing different security notions, and it would seem that you should ask the question which is the best definition, which is the right definition somehow. Of course, it's valid to explore the space of definitions and compare, maybe show that one is stronger than another, but definitions only make sense if one has ultimately a clear opinion why a definition is right.
Yeah,
what would justify a certain definition?
Yeah, I think that, okay, at this point, I'm not made my mind yet, but I think at this point, this could be a good definition. The one I gave at the beginning. Oops, where is it? Here. This could be a good definition because here I can characterize exactly for robust encryption scheme the functionality for which game-based and simulation-based coincide, the two notions coincide. And here we have, unfortunately, we have some impossibility results, which seems to be inherent. Of course, then I'm also exploring other, with Puya, Manuel, Angelo, and Vincenzo, we're exploring other definitions. And we point deficiency in each of them and we proceed by exclusion.
Well, I actually wanted to ask almost exactly the same question as Uli, except this possible suggestion, but I'm not sure. Wouldn't maybe, semantic security, you can view it, it's the right notion of security for passive attackers, in a sense it's kind of UC security for, I don't know, passive attackers or something like that. CCA is like security for active attackers. So is there some kind of maybe ideal functionality for functional encryption so that you can kind of see, so because maybe if you characterize which definition is equivalent to UC security, maybe for like passive attackers, whatever it means, which game-based or whatever simulation-based definition is equivalent, that might suggest what is the right definition, kind of answering Uli's question.
I just sent a mail to my students saying, try to phrase this in constructive crypto, because that I think is the language to.
Or constructive crypto, I guess that's another way to do it. Because it's as you said, semantics. Indistinguishability is also a natural definition, but given the problems, it's kind of unclear that it would compose, and I guess it wouldn't. So you would need something like that, but even that is, I'm not sure it's enough.
Yeah, so that's a very nice suggestion. Something that we could pursue and see if we can get some equivalence. Okay.
Second speaker.
Thank you.